set.
Okay, hello everyone. My name is Mark Gray.
And I'm Scheurich from Ericsson.
And today we're going to present some work that Intel and Ericsson have been doing to improve the performance of OvS-DPDK, particularly for telco use cases. So when you think of OvS-DPDK, I guess the primary value proposition is performance. And there are a lot of benchmarks out there that showcase the performance of OvS-DPDK. However, we do get some criticism really around the fact that some of our benchmarks, let's say, aren't representative of realistic workloads. But what is a realistic workload? I mean, we talked about this previously. OVS is such a flexible switch, general purpose, easy to program. It can be used in many different ways. And as a result of that, the bottlenecks in the switch can move around a little bit, and the performance characteristics for a particular use case can change. So in this presentation, we're going to focus on one of those particular workloads, which is, I'd say, representative of NFV, which is an L3 VPN with a very large number of flows. An NFV large number of flows. We stopped benchmarking at 500,000 flows, L4 flows. So we're going to talk about how we determined where the bottlenecks were, where those bottlenecks were, and the kind of optimizations we took in order to improve the performance. And then we're going to present some really compelling results that show significant performance improvements for a very large number of flows. And we'll talk about a bit about future work as well. So just pass on to Jan.
Thank you. Yes. So luckily, we've had a number of speakers that explained what network function virtualization is about. So I don't have to repeat all this. That's good. We can focus on the interesting part. So you've seen this picture. I don't want to bore you with the architecture. The really important thing is that network function virtualization is about running a lot of virtual network functions that have previously been running on physical appliances virtualized, and you can have any kind of type of function like firewalls, load balancers, deep packet inspection, content filter applications, carrier grade NAT, entire telco applications like, for example, an evolved packet gateway. And they come in a number of flavors. In the simplest case, it's just a VM. Then there are complex clusters of VMs that are chained in the data path that could even in the future be a container-based microservices architecture. But whatever, they all share this common characteristics that they have very high requirements on packet throughput, latency, and jitter. And in order to address this in a cloud execution environment, the compelling choice to use is OvS-DPDK as a data path because it promises to give the performance. The question is, how good is the performance of OvS-DPDK in these scenarios? And in order to answer that question, you really have to run meaningful benchmarks. And typically, the OVS benchmarks or any vSwitch benchmarks are rather simplistic, right? You have two physical ports. You feed packets from one physical port to the other. In the case of OVS, you often have a trivial pipeline, a single table matching on one or two fields, no packet modifying actions, just sending out on the out port, and that's it. And that's very nice because it gives you nice and flashy performance figures like 10 gig line rate with 64-byte packets and a single core. Good for marketing, but unfortunately not very helpful for answering the question how good is OvS-DPDK or any other vSwitch for that purpose when handling real NFV workloads. Let's have a look at a typical configuration for network function virtualization. Same compute node, but now traffic is coming from physical interfaces going to a virtual network function running in a VM connected through vHost user ports. But that's not all. In addition, traffic is typically encapsulated on the physical interfaces for network virtualization purposes, VXLAN, Geneve, you name it. To add more on it, for redundancy purposes, there's not a single interface physical, but there are typically two connecting the compute node to a pair of Tor switches in multi-chassis lug mode, and you run a bonded interface in between them. That adds a lot of complexity and multiple stages in packet processing, and we'll look at that later. When you look at the OpenFlow pipeline, it is programmed by an SDN controller. The pipeline can become arbitrarily complex. This is a real-world example that I've depicted here, coming from an open daylight pipeline for a network. So it's very difficult to estimate the performance of this when you run packets through it. The question is, of course, we want to answer that is how performant is it? But before we actually present our baseline measurements that we did on OVS 2.5 and some other vSwitches, I'll hand over to Mark again to have a more detailed look at the performance affecting factors in OVS.
So what are the things that affect OvS-DPDK performance? Kind of where are the bottlenecks? So this is a representation of the packet processing pipeline of OvS-DPDK. You receive frames from an interface, a physical or virtual interface. You then do a series of lookups in tables to gather actions which tell you what to do with that frame. Then you execute those actions, and then typically you send it out an interface or drop it or something like that. But at each point in this pipeline, there is a cost associated with that activity. And that cost is measured in cycles. And if you add up all those cycles, you get the overall cost in cycles for handling a single packet, and that gives you an indication of what the performance for a particular use case is. Because depending on your use case, and depending how you're configuring the switch, how you're sending traffic through the switch, that is going to change where the bottleneck is and how your switch performs. So here's some simple ideas of where how the cost varies in a virtual switch. So for example, if you're doing I/O or X or TX from an interface, the cost associated with reading or writing to that interface will vary depending on the type of interface you're reading or writing to. It might be more expensive to write to a virtual interface than a physical interface. Depending on the physical interface you're writing to and how efficient the driver is, it could be more expensive on one rather than the other. Jumping a bit ahead here, action cost as well. Obviously, it's going to be more expensive if your pipeline consists of more actions. So if you're pushing a VLAN tag and outputting to a port, that's going to be more expensive than just outputting to a port. So there's various things. Probably the biggest cost, I suppose, in the packet processing pipeline is the cost of doing a lookup, and we're going to talk a fair bit about this in this presentation because it's very important when you have to do a lookup for 500,000 flows. So there's some things that affect that. I'll talk about that in a little bit more detail here. Open vSwitch presents to the user an open flow pipeline. That's how you configure it. Open flow is basically a set of match action tables, wildcarded match fields, and you pass your packet through all those tables to determine what to do with it. That operation is very, very costly, and as Ben talked about yesterday, Open vSwitch tries to get around that by introducing flow caching. So flow caching saves some of your flows in other lower level tables. So in OvS-DPDK, there's 3 levels in that hierarchy. You have your open flow tables on the right. You have your mega flow cache in the middle, which is also called the datapath classifier. And you have your microflow cache on the left there, which is the exact match cache. So each of these tables have different characteristics. The mega flow cache is a single table that represents all the data paths in an instance of Open vSwitch, and that table is a match action table that can match on wildcards. Whereas the exact match table, again, is a single table it's an exact match table again, but it's obviously exact matching on the match side of things. And the performance of each of these tables is different, as indicated by this diagram. So ideally, you would want all your flows to match on the microflow cache, i.e. the exact match cache for the best performance. However, that's not always possible because that exact match cache is a limited resource. And if you have a large number of flows, 500,000 flows, it won't fit into that exact match cache. And inevitably what happens is you miss on that exact match cache, and you have to do a lookup in your megaflow cache, which is a more expensive lookup. So in this work, we focus on a couple of areas, and Jan will talk about why we chose those areas. But lookup cost is one big one. That's in terms of the lookup in the datapath classifier, the exact match cache, and also the associated cost of inserting and removing entries from those tables. And we also look at the TX cost and the recirculation cost.
Okay, thank you. So We took our real-life example of a layer 3 VPN pipeline to actually benchmark the performance of traffic running between two VMs on two different compute hosts, going over a VXLAN tunnel between them. So this is one of our typical cloud NFV infrastructure use cases. And we tested 3 vSwitches. We tested OVS 2.5. This work happened basically before the summer break. So OVS 2.5 was the most recent version out there. And then we compared the performance to other DPDK vSwitches. We had an Ericsson in-house high-performance vSwitch, also open-flow programmable, called Hippos. And we used the VPP 1606 out at the time. And layer 3 VPN pipeline matches on layer 2 and layer 3 fields only. And so if you look at the other two vSwitches, VPP and Hippos, they don't have the concept of a flow cache. And which means that their performance is dead flat over the number of concurrent TCP connections that we ran in the packet. I have some problems with the microphone here. Can you fix that, or 1, 2, 3? Yeah. Okay. I can speak up a little. Sorry. So what you see on the x-axis is the number of concurrent TCP flows that we send through the system, and we measure the million packet per second throughput at 64 byte packets with a single core. And the performance is dead flat for the two reference vSwitches at 3.2 million packets per second per core and 2.5 million seconds per core.
Grab the mic.
Thank you. Yeah, that's much better. And the behavior, obviously, as you can see, is very different for OVS 2.5. And the reason for that is that for the regime where we have few parallel flows, I need to go back a bit, right? The EMC is effective and accelerates the lookup, so we get competitive lookup rates. But the more flows we have, the less hits we get in the EMC. And it flattens out towards the right-hand side, and we are basically hitting the megaflow classifier performance at about 1.2 million packets per second. And that was kind of disappointing, right? Why would OVS 2.5 be so much slower than the other vSwitches, even though it had a concept of a megaflow cache, whereas the other ones actually did send every single packet through the pipeline, the entire pipeline? So then we concluded that there must be something seriously amiss, and because there could not be any fundamental reason why OVS would be so much slower. So that's why we had a bit more detailed look at where the cycles are being spent here. So with OVS 2.5, we have, let's say, 740 cycles per packet. And using perf-top, we attributed the cost of the individual function calls to the various areas that Mark introduced. And you can see here that the bulk of the cost is actually in the lookup. Flow extraction, EMC lookup, 24%, 40% megaflow cache lookup. That's enormous. And then there's another bulk that is 12.5% for the TX, much higher than RX, so there was also something amiss there. So we decided to focus on the lookup parts and the TX and try to find optimization possibilities. And let Mark take over. You have the mic. Good.
So, given that, we had a chat and we were talking about potential areas for optimization for these type of use cases. And we identified some ideas, and then we started to have a look at these ideas and try and implement them. The legend here, the kind of dark green tick is stuff that's already available in the upstream, and the lighter tick is stuff that we haven't posted yet. Most of it is complete at this stage, and we do plan to post it over the next couple of weeks. But we'll talk through some of the optimization activities we did over the last year or so. So the first thing was that, as I think was mentioned yesterday, the megaflow cache, the datapath classifier, is implemented using a tuple space classifier. And we thought about maybe using different table types for the implementation of the megaflow cache. In particular, we wanted to use a tree-based classifier that was available in DPDK for implementing ACLs. We took that, and so that tree-based classifier is a lot faster to do lookups than the tuple space classifier, particularly when the tuple space classifier has a lot of subtables, as some of my colleagues talked about earlier on today. And we integrated that into OvS-DPDK. It did give us better performance. The lookup was a lot faster, but the cost of modifying these tree-based classifiers, so adding new entries or removing entries, was very, very expensive. People may have saw some conversations in the mailing list. There were some ideas about how we could hide this cost, but in the end, we decided just to abandon that effort and look at optimizing the code that was already there. So one thing is to do a good hash table, you need a good hash. And in OvS-DPDK, by default, it uses some software hashes, murmur hashes, and they perform pretty well. However, it is possible to accelerate them using instructions on CPUs. So for example, on Intel processors, you have the CRC32 instruction, which implements a fast hash. So by using that, you can see a huge performance benefit, and not everyone is aware of that. It's probably not very well documented. I think we improved the documentation, but that helped in this use case anyway to improve our performance. Another thing is the cost of writing a frame to an interface has a certain amount of cost, and if you write more than one frame to that interface, you can amortize some of those costs across a batch of frames. So previously, OvS-DPDK did this. However, it was removed because there were some problems with that code a while back, and that did affect our performance. However, we have re-engineered that code and addressed some of the concerns with it, and we hope to push that soon to show better throughput when you're sending packets out on TX to another interface. Another thing we did is we looked at the code and we wanted to make sure it generally ran efficiently on our processors. So one very important consideration in this effect is how well it utilizes the CPU cache on the system. So we made sure that the code was written in as efficient a way as possible, in particular using as little cache as we possibly could, so we could be very efficient in that regard, and also making sure that all the data structures were correctly aligned to cache lines to ensure that we don't suffer maybe 2 cache misses to look up one structure. So we spent a good bit of effort doing that, and I know Banu posted some patches on that quite recently.
Yes. This one is not. No. To address the big bottleneck in the DPCLS lookup, I did some work already prior to OVS 2.6 release, and it's upstreamed. We have had another talk earlier today. The DPCLS lookup is a series of hash tables, and in the worst case, if you have n hash tables, you have to revisit all n hash tables to find a match. There can only be a single match, so once you have found that, you're ready. But if there are many subtables and you don't know and they are not in any particular order, you can be very unlucky. In reality, though, even though there may be very many subtables in the classifier, not many of them are actually applicable when you know the ingress port of a packet. Because packets coming from a certain ingress port typically only hit a few of these subtables. So the obvious improvement that could be done was to actually go away from the global DPCLS instance for the entire data path and create one for every ingress port. And as an additional optimization within that ingress port to sort the list of subtables, if there were many or multiple, according to hit frequency periodically. That's a very lightweight operation, can be done easily. And with that, we are actually able to, in all the scenarios that we have been testing, to bring down the average number of subtable lookups needed for a megaflow lookup to close to 1. That's the optimal value that you can get. So that has been really a big improvement for the megaflow classifier performance, basically 50 to 80% in performance improvement. And that work has been upstreamed, and it's already in OVS 2.6. We'll show you the effect of that in a minute. Then the next thing that we realized was that when you're looking at this strong degradation of the performance with a high number of parallel TCP flows, is that the presence of the EMC when it is thrashing is actually degrading the performance of the entire data path significantly. Because if you disable the EMC, you run the exact same workload, you get 30% better performance. So we wanted to keep the benefit of the EMC for few flows, but we don't want the negative effect when we are thrashing EMC. And the patch that we have implemented, and that is almost ready for upstreaming, for posting to the mailing list, is addressing this problem by doing a probabilistic insertion. So we don't unconditionally, every time we do a mega flow lookup, insert the packet flow into the EMC, but we do it only randomly every 1 out of 100, which cuts down the overhead of EMC insertion, which is the expensive part, by a factor 100, so it doesn't do any harm anymore. And we still have the good positive effect for the long-lived flows if there are not too many. So that has proven for those scenarios that we have been testing as a very, very effective measure of combining the useful effect of EMC for few flows with avoiding the negative effect in the other cases. And together with that, we have actually done some improvements on the usefulness of the PMD-STAT-show printout, which gives you some idea of about the utilization and the performance of the data path. I'll show you an example about that in a minute. The last thing that we have addressed here relates to tunneling. Tunneling today in OVS 2.5 and also 2.6 requires recirculation. On the ingress, when the packet comes and we detect it's a tunnel packet, the tunnel header is taken away, the packet needs to be reparsed, and then it goes to the inner bridge. That recirculation we cannot avoid. But on the egress, the solution today is the packet is encapsulated and it is sent into the underlay bridge, where it is then forwarded based on MAC address. So there's another recirculation there to actually handle the packet in the underlay bridge. And that is completely unnecessary because the OF proto layer knows already which interface the packet shall be sent out to. So it can directly generate all the actions needed to transmit the packet without a recirculation. So the patch that we have done here is to avoid recirculation on the transmit, so that we only have one recirculation on ingress, but no recirculation on egress anymore. And that basically concludes the list of the things that we have done in collaboration here. And I would like to show you the net effect of all these optimizations together. So just to remind you, this is our baseline, OVS 2.5, and we have done fresh measurements with a newer version of VPP, but the performance is basically the same as before. And let me show you what the performance is in OVS 2.6. You can see here we have significantly improved the performance, the baseline performance of the Megaflow cache. That is the right-hand side, and that is the area which is interesting for us in NFV because the systems are exposed to a large number of end-user flows. But we still have a significant degradation, and so we continue to improve on that. And if you look at the complete set of patches that we have been describing, this is the situation that we have today. You can see the degradation is much less than before at the high flow side of things. We are at roughly the same performance level as VPP. There, we still have a performance advantage on the low flow regime due to the EMC effect. In total, we have improved the performance of the EMC, let's say, to almost 4.5 million per second, and we are at 3.2 million per second for a single core in this complex setup with OVS 2.6 plus patches. So, which proves that basically the technology is there. All the vSwitches can use the same tools that are available. We are on par with the other vSwitches. Any further improvement that can for sure be done will probably, like the vHost user improvements that we have been discussing today earlier, will benefit all vSwitches. But we are now in a position in OVS to really be on the level that is competitive with the rest of the world. Cost breakdown, as you can see now, is much more even. The total cost of lookup has gone down to 50% instead of 70% as we had before. The total cost per packet has gone from 740 to 332 cycles. So the lookup optimizations have been fairly effective. Now the biggest chunk is the transmit, and it's mainly transmit to vHost user. So the vHost user interface, the transmit there, is one of the bottleneck areas, and that's something that we will probably address in further work. If you look at this example of the PMD-STAT show, this is the new PMD-STAT show, It has more information. It tells you, for example, what is the EMC cache fill level, and it tells you how many subtable lookups there have been on average, and it gives you a much better idea of the occupancy of the utilization of the PMD thread, because now we really count idle and busy cycles. So we can really give a very good estimate of how loaded the system is.
Clicker. Yeah, sure is. So I guess one of the issues with performance optimization is it never really ends. It just goes on and on and on. And I'm sure one switch will improve and then the other one will improve and it goes on and on and on. But we are continuing to look at other areas. So one of them is cost of extracting a mini flow. It was touched on yesterday. There is a kind of a set cost in OVS for every packet. You extract this mini flow for every single packet. And the thing about the mini flow is it extracts all these fields, and you don't necessarily always need them for every subtable when you're doing a lookup. So we have some prototype code at the moment that will actually build a mini flow extract function kind of dynamically. It kind of jits it depending on what the flow tables look like. And that's showing some benefit at the moment, but that's still work in progress. We're also looking at other actions. So we know like the decrement TTL action could probably be a little bit better. We're looking to optimize that, and we'll look at other actions that are in OVS and see what we can do there. And then other things. So VirtIO vhost is obviously a bottleneck, and I'm sure many people in this room have some grumbles about various aspects of the performance of OvS-DPDK, and we'd love to hear them, because I'm sure we can help, by working together, we can help improve them. So in summary, hopefully you've seen that OvS-DPDK is a suitable virtual switch for complex NFV pipelines. And even if it's not, I think with a little bit of effort, it can be optimized to help to fit into those performance requirements that you have. And in particular, I think collaboration with other members of the community really, really helps. We all bring something different to the community. And I think by working together, we can help improve the performance of the virtual switch. I'd love to call out all the people who actually helped on some of this code. There was a lot of people from Ericsson and Intel, but you can ask us afterwards and we'll point you to all the people for the individual patches. And that's it, if there's any questions.